So, all right. So yeah. So I wanted to discuss this the homework problem. I figure by now everyone's looked at it. Whether you've gotten it or whether you haven't gotten it, it's a problem that has. Did anyone, by the way, not get one? I made 22 copies. All right. Well, whoever comes in late can get it. Anyway, it's a beautiful problem, and it actually was something that just came serendipitously in the research of the graduate student who happened to be TA for this course. He was trying to do an Arndt-Eistert homologation on a CBZ derivative of glutamic acid and ended up getting something he didn't expect and literally had no idea what it was. And as the structure unfolded, it ended up being a really beautiful structure, but also just a beautiful example of once you figure out a structure, being able to try to understand conformation, stereochemistry. And so that's what I'd like to share with you today. It's a challenging one. I think it also has depth so that even if you've gotten it, I hope you'll appreciate the additional perspective. So okay, so if the basic inspection of it, we have a molecular formula of C15, H17, NO5. That means you have 8 degrees of unsaturation. We knew there's a CBZ group in there. And so the CBZ group can account for 5 of them. And so we still have a couple of other things going on in there. So I'll just say that that's 5Du. And it's pretty obvious once you see the CBZ group, and it's not going to end up telling us a whole lot. So, okay, the IR was interesting. You see an NH stretch at 3363 broad. You see a couple of peaks in the carbonyl region, one at 1732. 1732 is certainly right in the region you'd expect an ester. The other one is at, let's see, the other one is at 1696. Carbamates are like amides, right? So you've got we know we have a CBZ group. So carbamates are like amides. The nitrogen donates into the carbonyl, so that shifts it to lower wavelengths. So that's pretty reasonable to be with that. NHs often have clear bends in the IR spectra, and so you can see an NH bend at 1531, and that's pretty prominent. That's right down in that region that I say, well, you can't do too much with, but if you know what you have, you can sort of pick stuff out. So NH bends kind of fall into that region right below 1600. All right, what I'd like to do at this point is to attack the spectra here. And so I've made an abridged version of the problem. I figure this is good. Even if you have your homework problem handy, you can feel free to annotate this and follow along with me. And so the general paradigm that we've been using in the class for structure solving is once you get the basics of the structure, once you get the basic analysis of figuring out something about the formula, figuring out degrees of unsaturation, looking at the IR, we're going to look at the NMR and letter the peaks, and at the proton NMR and letter the peaks, and at the carbon NMR and number the peaks. And we'll work our integrals, and everything's pretty straightforward on the proton NMR spectrum, right? We have 5 hydrogens for peak A, clearly associated with our CBZ group. We have 2 hydrogens for peak B. Then we have a bunch of peaks that are 1 hydrogen. Then we have 4 peaks that are close together, 1 hydrogen, 1 hydrogen. Here you have to split your integral, so the relative is 2. You can just sort of divide as best as you can between the peaks, and it becomes 1, 1, and 1. You can also, in some of the peaks, see a certain degree of tenting in toward each other. So immediately when I look at, for example, the doublets of D and F, I look and say they probably are tenting into each other. They're probably diastereotopic protons. Also, you see a big coupling constant, right? You can get a pretty good idea of what a 7 Hertz coupling constant is from, you know, a lot of the patterns here, and this looks a little bit big, so this is probably a geminal coupling constant. We have these two very interesting doublets. So in addition to these doublets here of D and F, we have these two very interesting doublets of G and I. We're going to see, and they're going to, I think, I think they're going to give us problems. I think they've probably already given us problems in placing this group when you've worked this on your own. They're interesting. You have a very small coupling constant. They're tented into each other. They look like they might be a geminal methylene group, and yet the coupling constant's very small. Then we've got some multiplets over here, another multiplet, and another multiplet. And there, we'll look at those in more detail in the end if we have time, because there's some really beautiful analysis associated with them. All right, carbon NMR, we see 13 unique resonances in the C13 NMR. We can just number them. Ten and 11 are really, really close to each other. They're about 1/10 of a ppm apart in the carbon NMR. As we come into techniques like HMBC and HS and HMQC, it's going to be really tough, no matter how you expand, to resolve at that level. Remember, I said you generally get about 1024 slices with zero filling and so forth in the F1 domain, and your digital resolution is generally about 4/10 of a ppm, so you may not be able to discern them. If you were in a situation where you had to discern two resonances, one of the easiest ways to shift things around is just to take a spectrum in, well, specifically in deuterobenzene. Deuterobenzene induces magnetic anisotropy from the ring current of the solvent, and very often if you've got overlap like this, you'll shake things up enough to spread them out. Deuterobenzene or deuterotoluene are very good choices. We didn't here, and it's not necessary to solve the structure. We'll see the one point in the HMBC where there's some confusion actually disambiguates itself because it becomes pretty clear which is which. All right, so we have all of these peaks. Let's see, these guys here are quats. These guys are methynes. 7 and 8 are CH2s. 9 is a quat. 10 is a CH. So if you look very carefully, you can see we have a CH over here, and then we have CH2 over here. If you look really carefully, you may notice that it looks like we even get a little bit of the CH2 coming up over here. So 10 comes up here. And it looks like you may have a little bit of a hair for 11. Remember that the depth technique relies on an average J value. We're going to see that this is part of a ring that doesn't have typical J values. So it shouldn't completely surprise you that your depth isn't quote perfect. 12 and 13 are CH2s. All right, so that takes us through our preliminary analysis of the proton in carbon. Where I like to go next is to the HMQC spectrum. And again, I try to be really fastidious about transferring our labels. And this axis here is going to become our Rosetta Stone. It's going to become our workhorse in the problem. So I go and I just transcribe. And the goal, of course, is to correlate and figure out what's what and get our letter and number assignments together. G, H, I, J, K, and L. I'm going to get a different marker here. This one's getting mashed on the tip. All right, so we can go through very quickly. 4 to 6 are associated with A. 8 is associated with B. C doesn't seem to have anyone partnered with it. You've got a little broadness to C. C is pretty clearly our NH group over here. 7 is associated with D, 10 with E, 7 with F. So those guys were indeed diastereotopic. You can see things. You can see things over here. As I said, it's very hard to disambiguate 10 and 11, but I think it's pretty obvious since we know that 10 is the methine and 11 are the methylenes. I think it becomes pretty obvious which one is 10 here and which one is 11. So we have 11G and 11I, and then 12H and 12J, and then 13K and 13L. So that gives us, so this upper axis now really gives us our workings of the problem for putting pieces together. And the first thing is going now to be to use the COSY to build up the fragments that we can. Then we're going to want to keep in mind what we don't know, and then try to use HMBC to put those pieces together. All right, so I come in at this point to the COSY, and again, I very, very slavishly transcribe my axes. I always find it helps me avoid problems just by saying things to myself out loud. 4 to 6A, 8B, we have C, we have 7D, we have 10E, we have 7F, we have here 11G, 12H, 11I, and 12J, and then 13K and 13L. And I'll do the same here, 4 to 6A, 8B, C, 7D, 10E, 7F. Then I have G, H, I, J, 11G, 11I, 12H, 12J, 13K, 13L. All right, at this point, we want to start to work our way through the COSY. It doesn't really matter where we begin. Since the spectrum is symmetrical, right, we have our diagonal running along here. I just pick one side of the diagonal. If there's anything questionable, I check for a correlation on the other side just to see if I see anything. We do seem to see a little cross peak here between 4, and I honestly didn't try to disambiguate which it was, so I'll just say 4 to 6A to 8B. Now that's kind of interesting. So I'll start over here. Here's our benzene ring. We're 4 to 6A, and our CH2 is 8B. And this is kind of interesting because you don't normally see any sort of obvious splitting between the orthoprotons and the methylenes, and yet you've got a very small benzylic coupling, less than a hertz, so it's not going to give you a splitting. But in the COSY, if you've got a big peak like this singlet here, you may see a cross peak for it. It's not a big deal. You notice this coupling if you take a compound like toluene. You won't see the methyl split at all, but the methyl on toluene is ever so slightly broader than another methyl. So say if you had a methyl ester or methyl ether in the molecule, that methyl singlet would be taller than the methyl in toluene because that toluene is getting a minuscule little bit of benzylic coupling, too small to see, less than a hertz. So no particular consequence. Now we're going to come along, and of course that's part of our CBZ group, and we know our CBZ group, so I will just continue over here. And the next peak that we see is a cross peak that involves that NH, right? That NH is C, and so we see C to 10E. And so that C to 10E peak basically takes us over to the methine over here, and we're starting to build up our chain. There's nothing else that C is crossing with. The next cross peak we see is a trivial one. It's 7D to 7F, and that's that geminal cross peak. Your geminal cross peaks tend to be very strong. We don't see any other cross peaks off of 7, and that group is going to be a problem to us. As we continue, we see we have some cross peaks here. Our 10E is crossing with 13K and 13L. And so that's going to allow us to build our chain. Oops. Questions or comments at this point? Yeah.
The CBZ, how do you know that was attached to the carbon 8?
To the carbamate? Ah, okay.
Carbon 8. Sorry, carbon 8.
Oh, how do I know? Well, we have this cross peak here that's kind of cluing us in that we're seeing this very small benzylic coupling.
Yeah. So and then how do you know that the carbon 8 is attached to the oxygen?
Oh, because taken as a given was that we had a CBZ group in the molecule. It was part of what was, I think it was listed in the.
Yeah. And we see cross peak between 6 and 10, so that's why we don't see 10 as an extra.
In the HMBC. Yeah. But I think in just the description of the problem, I said there's a CBZ NH.
Right, you didn't say which like if it was 8 or 7. It could have been 7.
Ah, I see what you're saying. Well, at this point, based on this cross peak, I'm kind of clued in. Now, it's interesting. We know that the molecule has a stereocenter. We see diastereotopic methylenes. Every methylene in the molecule is formally diastereotopic. The CBZ group could appear as two doublets forming an AB pattern, or if those doublets are exactly at the same position, if the two protons are coincident, then it appears as a singlet. So it's actually probably right near a stereocenter because we have a carbon that has 3 different things on it, and it's certainly possible they're coincident. If I took the spectrum in deuterobenzene, it wouldn't surprise me if I saw an AB pattern with 2 doublets tenting into each other. So I'm not going to make much of that assignment. All right, as we go through and continue, we have mostly trivial NOEs. So for example, in this trivial cross peaks in the COSY. So for example, these 2 cross peaks here are respectively 11G to 11I, which is just a geminal coupling, and 12H to 12J, which is just a geminal coupling. But then we get a couple of useful ones over here. So we see 12H to 13K. We see 12J to 13L. And the strength of these cross peaks, I mean, here we see a teeny tiny cross peak associated with a very small coupling constant. The strength of these cross peaks reflects the magnitude of the coupling constant and the height of the peaks. But that allows us to complete our chain. And so we go to C12, H, HH, and HJ. All right, so that pretty much completes the information that we get out of here. We have one more trivial geminal coupling, 13H to 13L. See, this is why I love going through the HMBC first, because I really end up not getting myself sweated up over duplicate information. I end up not getting myself sweated up over trivial information. We very quickly get the information we need. Now, at this point, we can start to make a little bit of a scorecard here. So we still have our issues of C1 and C2 to resolve. We have our issue of we don't know what's happening with C7, HD, HF. We've got our quat of C9 that we don't know about. We have another isolated methylene of C11, HG, HJ. That's the one with the funny small couplings on it. And we have 3 oxygens. And we should keep in mind that C7 is pretty far downfield. In the carbon NMR, it's showing up at about 70 parts per million. In the proton NMR, we're seeing these 2 resonances here around 4 parts per million. So I think pretty clearly C7 is probably attached to an oxygen. Now we just have to figure out how to put it in. So at this point, I'm going to turn to HMBC and try to figure out how to nab the pieces. And again, I'm going to be very, very mechanical in the whole process to help avoid making mistakes. I just go 1, 2, 3, 4 to 6. I'm not going to stress about assigning 4 to 6. I could zoom in if I wanted to and figure out which one's the ortho one and so forth, but I'm not going to stress about it. It's just not that important in terms of the nature of the problem. 7, 8, 9, 10, 11, 12, 13, and here's 4 to 6A, 8B. C stands alone, 7D, 10E, 7F, G, H, I, J with 11G and 11I and 12H and 12J and 13K and 13L. All right, so I'll start off of here. We have carbonyl number 1. I mean, 1 pretty clearly is a carbonyl. It's not a ketone, not at 170 ppm or thereabouts. And so we look at this. Let's see. We have 1 to 7D, 1 to 7F, 1 to 12H and 12J, and 1 to 13K. All right, so if we're trying to build up a chain over here, and we have 1, and it's got to be an ester group. It's crossing with 12. It's crossing with 13. That's pretty much going to put it right over there. It's crossing with 7, and we're pretty sure 7, right where it's at, has an oxygen on it. So it comes through. We've got an oxygen, and we get our C7HD HF. And so that's a really useful example of using HMBC to build up our structure.
So once we determine that 12 and 13 are next to each other, we know that we can see that 1, 2, 4 bond coupling is our limit. So
well, 3 is normally the limit. So we go from the hydrogen on C to C is 1. From C, 13 to 12 is 2. And from 12 to 1 is 3. And here from the hydrogen on 7 to 7 is 1. From 7 to the oxygen is 2. And from the oxygen to C1 is 3. I kind of played around if there was any way I could think of putting the carbonyl here, but the only thing, and saying maybe this cross peak came through here, but then I would have had to tie up this valence as well, and it would have been game over, because I would have had to basically go around here. So there really is no way to build up this structure that I can think of.
So will HMBC always go through heteroatoms?
HMBC goes through heteroatoms, but remember the big caveat is you're not guaranteed to get an HMBC cross peak. Yeah, there's nothing special about heteroatoms. It's just going through the electrons making up the bonds.
So don't rule it out if there's an absence of it, you're saying?
Don't rule it, exactly. So the presence of a peak says 2 or 3 bond connectivity. We saw one example of 4 bond, and if you have allylic intervening allylic double bonds, you might have more. But basically, I'd say don't expect it to ever be more than 3. So it's basically 2 or 3.
I have a quick question. Cross peak between 1 and I, do you rule that out and you'll say that 1 is crossing with
1 and, oh, okay, here, 1 and I. I can't rule out 1 and I. What I can say from the shape of this peak in this dimension is clearly when you look at the lineup on this. So peak 12J is wide. Peak 11I is narrow. So when you look at the lineup, it clearly lines up. If I've laid my grid on there correctly, it clearly lines up with J. I can't rule out that that little lobe of the peak isn't also a cross peak of the I. I just can't discern it from there. And I suspect there's just about no way I could do this. If I didn't run an inverse detected experiment, and I ran a carbon detected experiment, remember I talked about het core and long range het core, then I'd probably get the resolution, but the signal to noise is incredibly bad in that experiment. If I really wanted to determine, as I said, I would probably use deuterobenzene as a solvent and see if I could shift things around. There's also a possibility of using lanthanide-induced shift reagents that create a paramagnetic, that are paramagnetic and shift things around if I really needed to, but I'd probably first try deuterobenzene. Anyway, this is what I know thus far. Other questions or comments at this point? All right, so continuing along here, not that I think there's any doubt at this point, but we see a cross peak from 2 to 8b. And so if there had been any doubts about what our relationship was over here, now we have it because our 8b goes again through the oxygen. It's a 3-bond coupling over to this carbonyl. We get some more cross peaks off of the benzene. This cross peak just by distance here to 8b is going to have to be the ortho. Honestly, I don't care at this point to assign my ortho, but if I wanted to, I could assign which of these guys was the ortho. All right. So let's continue on up into this region here. So the next one that's kind of interesting is we have 9 to 7F. Now 9 was one of our problem children because we've taken care of 7, we've taken care of C1 and C2. We've taken care at this point of all but one of our oxygens. So we don't have a whole lot left to play with. We have 2 valencies left on the molecule, and we have just 2 carbon atoms, and we have an oxygen atom, and so we get this cross peak with 9 and 7. And it's interesting because the one thing that we know at this point, we know that carbon 11 can't be attached directly to carbon 7. Because if carbon 11 were attached to carbon 7, we'd be seeing J coupling. I mean, a methylene next to a methylene has got to give J coupling. So at this point, we have to attach carbon 9 over to here. And we're kind of stuck in the same position here. We can't be attaching carbon 7 over to carbon 10. So we really are stuck in an interesting position about how to put this together. And it's going to require a little bit of thought, and I'll show you this at the end. Everything else that we get from this is trivial. We get 10 or 11 to 7F. So can't be 10. It's got to be 11 here. I mean, it can't. If it's 10, it's got to be going through here. So you're basically now starting to be left in a puzzle situation. We've got to get over to here somehow. We've got to isolate this. We have valencies on this carbon that we need to fill. And so the only way to fill it is going to be to go ahead and have C11, Hg, Hj attached over here. And we have one oxygen left, and we're not going to get any more useful information from the spectrum. We have to use our smarts to this. We've got 10 to 12H here. That doesn't really tell us anything that we didn't already know. We've got 9 to 13K. OK, well, that's consistent with this connection here. Let's see, we have 10 to 13L. That doesn't tell us anything we don't know. We have 13 to 12H and 12J. That doesn't tell us anything we don't know. And so we're left here with one oxygen and two valencies. And the only place to put that oxygen is over here as an epoxide.
Is there any reason why 9 doesn't show cross peaks like 10 or anything?
Geometry. So methynes are the worst. So two-bond couplings are all over the map. The J values can be all over the map. The oxygen and the hybridization probably make the J's smaller here. But there's no guarantee of seeing coupling. The one that I'll say is guaranteed, 3-bond couplings off of a methyl group. Isolated methyls are fantastic because the hydrogens point in all different directions and they rotate. So a 3-bond coupling off of an isolated methyl, I'll say you'll always pick that up. In other words, if you have an isolated methyl like so, not in this molecule, but in others, and you have a cross peak off of it, it may be a 2-bond coupling, but you're definitely going to pick up your 3-bond couplings off of an isolated methyl because you're always going to have a good Karplus angle. 3-bond couplings from methynes are the worst because if you are no way guaranteed to pick it up because your Karplus angle may be 90 degrees. You may end up having no coupling. And epoxides are confusing for a couple of reasons. So if you look at oxyrane, the parent compound, in the carbon NMR, and this is one of the reasons you have the Pretsch book, you'll find, well, first of all, of course, your J's are small, but you'll find that in the C13, it's about 40 ppm. I think it's 39.5. And in the H-NMR, it's about 2.5 ppm. I think it's 2.54 ppm. Oxyrane is very weird. And it's not specifically the SP, the hybridization, the angles, because if you go to oxetane, the 4-membered ring one, things go in the other direction, and it's a little too far downfield. in the proton NMR and a little far downfield in the carbon NMR. So that's one of the things that throws us, because we're not expecting 11 I and G to have an oxygen attached. And yet we're forced into reaching that conclusion by the fact that we just use up all of our valences and use up all of our atoms. One more question I saw.
Also, like, I keep seeing that crosspeak between like I, like 13 to I isn't. Because I mean, we see three crosspeaks I 13, so we see 13 to H.
Whoops, this is, did I do this wrong? This is,
J.
this is, wait, G, I. Whoops, let me correct this. I, and that's I over here. All right, G, yeah. Okay, so you're seeing a cross peak.
13 to I.
13 to I. I guess I'm just.
I mean, we see the 1 to 3 to J. But then
So which cross peak are you referring?
so like, I guess I'll just like this one here.
See, no, but you see, okay, let's look, all right, so let's look at that multiplet. It was the question was, what was the glutamic acid derivative? It was the anhydride of glutamic acid. All right, so let's take a look at the peak here. So here's the peak we're looking at for the doublet. And you can see, so we've got this pattern of something that we've got a line, then there's another line buried right under here. And so we simply cannot tell. Anything that was just off of peak I here would just line up with this. So we're seeing ones that line up with both. And so we just can't tell if we have anything unique.
So then why wouldn't I just do this one cross peak if it's just crossing with that one over there?
Why, if it was just crossing with which one? This one?
Yeah.
Because this one comprises peak here and peak under here. It is purely overlapping.
Okay.
And so, you know, you can see that the last part of this peak is overlapping. And this is the problem with ambiguity. You have to be able to deal with ambiguous data. And, you know, the way I dealt with it here is I said, I just can't tell. It's 10 or 11. But here, I could tell that I couldn't tell if part of it was with 11I, but I certainly could tell there's one with 12H. All right, at this point, I want to redraw the ring, and then I want us to work on the stereochemistry of this compound. All right, so to redraw the ring, let's just go ahead. It's a 7-membered ring. And we have an oxygen. I think I will write it bigger here so we all get it. All right, so here's what we have at this point. We have a 7-membered lactone ring. we have an epoxide. We have a spiral ring fusion. I think this is the first spiral ring fusion we've seen in the class. We have two stereocenters in the molecule. So we've got to get those stereocenters relative to each other. And in a spiral ring fusion, understanding the conformation of the ring is going to be even more important than it is in, say, a bridged bicyclic or a fused bicyclic system, because we really end up having to figure out which hydrogen is close to which and which way things are pointing on the ring. So let us begin with the nosy spectrum. And we're going to have to assign our resonances. All right, let's see. And so I think I'm going to start. And we're going to have to make diastereotopic assignments of our resonances. So I'm going to give us a clean slate on this so that we can deal with things. Now, one of the things that you've got to keep in mind is you cannot assign the absolute stereochemistry of the molecule. Simply isn't possible, which means you just need to pick a stereocenter, assign it, and assign everything relative to that. In this case, I happen to know what the absolute stereochemistry was because I know which enantiomer of glutamic acid we started with, so I'll actually give you the right one. So I'm going to redraw everything here in a way that's going to allow us to put in stereochemistry. So if you want, you can feel free to follow along with me. 1, 7, 9, 10, 13, 12. And so arbitrarily, I'm just going to pick HE as pointing up. Doesn't matter. All right. And so now we have the problem of the epoxide that we've got to deal with. All right. We have two expansions of the nosy for you. I will start with the first one, and then we'll move into the second one just to make it a little easier on us. All right, so the things that are kind of interesting, we see the whole 4 to 6A to 8B bit over here. That's just the orthoprotons off of here. We have a little kind of something here off of the CBZ. I'm not even going to use it, but I'll show it to you in a second. We see 8B to 11G here. If you're confused because it's a pretty small peak, you can look. We have this stripe of T1 noise off of the big peak here, off of 8B. If you look, you can see symmetrically that it appears over here. So this is 11G to 8B. We're not getting. So what we're getting is it's off the CH2 of the CBZ, and it's going to be to the CH2 of the epoxide. But I'll show you, we're going to see two more peaks, one off of HC and one off of HE, that will give us that same information. So we don't need to stress over that. All right, let's move in to the expansion of the nosy, and we'll find everything that we want and need over there. All right, so off of let's see, where should I start? So off of C, we see 11G. So let me transcribe my letters. C, 7D, 10E, 7F, G, H, I, J, 12, 11 and 11, 12 and 12, 13K, 13L. Let me just do the same here really quick. 7D, 10E, 7F, 11G, 12H, 11I, and 12J, 13K, 13L. All right, so a picture is going to emerge as we start to work this. So we've got 11G to C and 13L to C. So the fact that we're getting all right, so we've got 13L over to C, and so it's sure suggesting that we have a cis relationship over here. It's not proving it at this point. And then we've got 11G to C. So that's interesting because we have our epoxide over here. We don't yet know the stereochemistry. This is going to prove to be the toughest part of things. But we've got this relationship here. And let's see, where do we continue to go? All right, so let's continue to work our way and just assign our resonances. So we've got 10E, a little hard looking in here. We've got 10E to 7D. This one's trivial, 7D, 7F to 7D. That's just a geminal. But 10E to 7D. See, this one, this is really interesting because I can't be sure these two are cis here. If I see one big NOE, so H, actually I can be sure they're cis because I don't see an NOE between C and K. If I saw an NOE between C and K and this one was big and this one was little, I could be sure they're cis. But if I don't see an NOE, that also, I mean, basically you have to be making comparisons here on geminal ones for figuring cis. But once you're moving over to a 1-3 relationship, the only way that you can get an NOE of any size like this one, like this 10E to 7D, is for them to be cis and probably in an axial relationship. So that one here is really, really useful because it gives us a stereochemical relationship, and it's going to start to give us a confirmation. All right, as we continue, we're going to see more like this. So we see 12J to 7D. And that's interesting because that continues to take us in this non-adjacent relationship business here. And so we see that one. That's giving us this. And if we continue to go, we're going to see a couple more that are very useful. Let me show you. All right, so we see 13K to 10E, 13K to 10E. So that's kind of corroborating our earlier assignment on this, the stereochemistry of those diastereotopic hydrogens. 12J to 10E, and you can kind of now see, if you look at the alignment here, you notice where this cross peak is centered, David? See where this cross peak is centered here? And you notice where this one is centered here? See that little offset on them? So now we can start to get some distinction here. So we see 12J to 10E And we can go ahead and say, all right, 12J to 10E, that completes things around here. And then we're seeing 11I to 7F. And we're seeing 11G to 10E. So this is interesting. So we're continuing to make this network of NOEs over here. Most of the remaining ones are trivial. I think we see one more. There's a bunch of geminal NOEs in here and vicinal NOEs in here. And yeah, so that pretty much gives us our key NOEs. What I want to do at this point is to build up the conformation of the molecule. And I was joking last time. Actually, let me do this over. I'll do this here, then we'll end up pulling the board in front of it. All right. I was joking last time that I can draw two types of rings. Let me show you how far those two rings will get you. So if you treat a cycloheptane ring like a cyclohexane ring, and you say basically, you can think of it just as an extended cyclohexane ring. That will take you pretty far in terms of your relationships. And we see our HE, our HJ, and our HD all have these nice NOEs to each other. It's this ring of NOEs that I've written over here. And that really superimposes very nicely on this model. That puts our HC here sitting in an equatorial position, equatorial-like position. It puts our lactone over here, puts HL over here, HK over here. Now we last have our HF over here. Now the last thing we have to deal with is our epoxide. And our epoxide, the way I've drawn it, you probably won't be that experienced at this point, but the way I've drawn it now, I think you can end up seeing. We see an NOE from HI to HF. We see NOEs from HG to HE and HC, and also to the CBZ group. And so that puts our methylene out here, like so, for the epoxide. It gives us our epoxide stereochemistry, and it assigns, so that sets this stereocenter, and now we just have our specific resonances, and so pointing out is HI, and pointing back is HG. And if you look at a model, and let me very quickly, if I can make my computer talk to the projector, I'll pop that up. If not, I have a printout. See if it warms up quickly enough. They talk to each other. Give it one moment. Here it comes, and if not, all right. I'm gonna pop.
It just popped up for a second.
Ah.
There it is.
All right, great. Then let me. All right, so this is the model here. And what's nice is you can, look, if you're experienced with these types of rings, you can probably do this on pencil and paper. But building a model to influence your thinking and being able to query that model and say, okay, what distance do I expect in this model? Is this consistent? Is so valuable. The other thing you can get better than I can do with my pigeon drawings here is your coupling, your dihedral angles. And it turns out that these are really, really beautiful when you look. There are 3 multiplets here that are very, very dissectable in this structure. And I'll just flash this up and conclude us with this here. So the three multiplets that I think are just beautiful to analyze is you can work through, this multiplet is a D with 14.9, 8.2, and 1.8 hertz coupling. This one's a little tough. If you push yourself, you can get it as a DDD with 14.3, 8.1, 4.5, and 1.9. And this one, if you really push yourself, you could call it an apparent QD with 3 big couplings. It's a DTD with 13.9 for the big 11.7 and 1.8. And I felt very, very proud of myself because after working very hard on those multiplets, I just plugged them in my first order simulation, and they really matched like a fingerprint on that. So then you can correlate that with your confirmation. Yeah, no. Well, actually, I probably learned a few things from people in class on this one. Right, mine's more symmetrical because it's only first order. All right, I've kept you a long time, so we'll talk this afternoon about Valhalla and some of the others.